26. I have two charges, and I'm going to move one of the charges from a distance r initial away from Q1 to a distance r final away. So I'm just moving charge Q away from charge 1. Now, charge 2 is has a force acting on it from charge 1. There's an electric force. They're both charges. There's an electric force there. The electric force is conservative. So bringing back the equation that we just inherently love. The conservative work is equal to the negative change in potential energy. So what we're about to do is derive the formula for electric potential energy. So this is the integral of F dot dr, which is U final, negative U final plus U initial. What is the force, or what's the formula for the force acting on Q2?
K Q1 Q2 over RI squared? Like the electric force?
Oh, it's over R squared, just generically for now.
Okay.
So this becomes, yes, it is electric force. So this is K Q1 Q2 over R squared R hat dot, I guess R1 hat. Because this is the force on charge 2. What is the direction of dr? Because I'm doing a dot product here and I have two vectors, so I mean R1 hat is away from R1, but what is the direction of dr? To R1 hat? I hope not, because then potential energy is 0.
Be parallel.
Pardon?
Parallel to R1.
Yeah, parallel one. Because I'm moving in that direction, that's the direction of dr. It's the same direction as R1 hat. And so I can now break this down into K Q1 Q2 over R squared dr. From some R initial to R final. Well, KQ1, Q2 are constants, so I can just pull that out. So I got KQ1, Q2 times the integral of 1 over R squared dr from R initial to R final. So what's the integral of 1 over R squared dr?
Negative 1 over 2 square root of R. No, negative 1 over 2 R squared.
Negative 1 over
No.
2 R squared, no. All right, so let me rewrite that.
And that's not one natural log.
No, 1 over R, get you with the natural log.
Okay.
This is R to the negative 2 dr. I don't know if that will help you.
Negative 1 over R.
Yeah, negative 1 over R. You add 1 to the exponent and then divide by the new exponent. So I got negative 1 over R from some R initial to R final, which will end up being K Q1 Q2 negative R final minus negative K Q1, Q2 over R initial. And that's equal to negative U final plus U initial. Therefore, the electric potential energy, what is a formula for electric potential energy, which will make that true?
Change in, electric force.
No.
KQ1, Q2 over negative KQ1, Q2 over R plus constant.
All right, so we got the plus constant there. There is an issue though. There's a mistake.
What is it? Oh, sorry, it's positive
Yeah, positive.
because
Yeah, the negative and the negative already there. That's positive. Positive. Typically, they just write KQ1, Q2 over R, but you can always add a constant. Now, at some point, when I'm writing down the formula for electric potential energy, I will put down R squared in the denominator because I am so used to doing the force formula that I will put down R squared. Please correct me sooner than later. Just remember, it's not Precious's job every time to correct me. Actually, it shouldn't be any of your jobs, but you know, reality is, I'm gonna do that kind of thing. So if I take a charge here, if I have a 5 nanocoulomb charge, and I have a -3 nanocoulomb charge, and I'm gonna claim that when electric potential energy equals 0, when R is equal to infinity, and these are 2 meters apart, what is my electric potential energy of this system? Well, 9 times 10 to the 9th, times 5 times 10 to the -9th, times -3 times 10 to the -9th, divided by 2. Recognize that what this does right here is that sets my constant equal to 0. Because when R is infinitely large, this fraction here is equal to 0. And so, since the potential energy is equal to 0 at that point, the only way it works is if the constant is 0. It would have been convenient if I had done at least one even number in the numerator. All right, 45, 90, 135, 62.5, negative 62.5 times 10 to the -9th joules, or negative 6.25 times 10 to the negative. But
I got
10 to the
negative,
-8. I'm 10 to the -8.
negative 8.
There, I got -6.75 times -8.
Yeah.
Okay, so that's right there, that, with the wrong way there,
And it's 6.75.
that's why.
7.5. There. And it's energy, joules, because I'm dealing with SI units up here. So if I took that, if that charge were an infinite distance away and I brought it into within 2 meters of my 5 nanocoulomb charge, that's the amount of work I would need to do to move it that far. And the reason why it's negative work is the fact that they're automatically attracted, so to bring it there, I would at a constant velocity, or a constant speed, I should say, I would need to be pushing against its movement, because it's being attracted. Let's add a third charge to it. We don't necessarily have to solve it, but at least know how to set it up. So let's put a charge here. We'll make that 2 meters away and make that 2 meters away. And let's make this 4 nanocoulombs. How would you find the potential energy of this system? Because I have 3 charges, but my formula has only 2 charges. So we want to take a shot at it?
Do we add them? Do we add the potential energy?
Yeah. How many potential energies are we adding?
Would it be 2 different ones? Would it be 2 different ones?
Which 2?
Like the 5 and the 4 plus the 4 and the -3?
Plus,
The 5 and the -3.
you take each combination of 2.
Okay, so it'd be 3.
Yeah, so we already done this one right here, and then that one, it's gonna be very similar to this. So plus, do keep track of the plus and minus signs. There's no direction here, but the negative sign does have meaning. Typically, negative potential energy in a situation like this means that there's an attraction going on. So plus 9E9, 5E -9, 4E -9. Over 2 plus 99, -3E9, sorry, -9, 4E -9, 2. And then this point is just a calculator exercise. I have done problems like this where I've just said set up the equation, you don't actually have to solve it, because once you get there, I'm assuming that other than careless errors, you know how to do it. All right, given the time, I'm just gonna set up for this next piece, we'll deal with it next time. But sort of summarizing what we have so far. Two charges, 1 charge. That's the word charge there. Vector, scalar. If I have 2 charges and we're talking about a vector, we're dealing with electric force. The units, the SI units of electric force, and it's technically the magnitude, is the Newton. If I have 1 charge and I'm talking about a vector, I'm dealing with the electric field. And the unit of the electric field, the magnitude, is newtons per coulomb. If I have 2 charges but I want to deal with scalar quantities, we're talking about potential energy here. And the unit of potential energy is the joule, the SI unit. There's obviously a gap here. And that is what we will deal with next week. You'll actually deal with it somewhat on Thursday. but there is a missing piece here. And in terms of electricity, this piece right here is the one that you probably are most familiar with. Let that be a cliffhanger.
To do with voltages?
It does have to do with voltages. However, the missing piece is not voltage, but it's very much related to it.
Current, is it current?
Pardon?
Is it current? No.
Is it curl?
Yeah.
Current.
Current, no. It's related to
Is it
current,
watts?
more related to voltage, but, pardon?
Is it watts?
No. Get farther away.
Is it related to voltage?
It is related to voltage. Which, it's connected enough to voltage, that's how you're most familiar with it. But there is a very, real difference between the missing piece there and voltage, so I don't want to equate them quite yet. Or actually, I don't ever want to equate them, even though some textbooks will.